Let's start by reviewing a particular property of linear functions. So if we have a linear function y equals mx plus b, and we want to know where the x-intercept is, the x-intercept is where the line crosses the x-axis, and every point on the x-axis has a y-coordinate of 0. So if you want to find the x-intercept, you just have to set y equal to 0. And you can solve this for x. You can subtract b from both sides and divide both sides by m and get minus b over m. Let's try that for a few functions, a few linear functions. Let's look at three of them. Y equals x plus 3, y equals 2x minus 1, and y equals minus 3x plus 5. So in every case, to find the x-intercept, all we have to do is set y equal to 0 and solve for x. So the y-intercept for the first one is x equal to negative 3. So it crosses the line at negative 3 comma 0. If we do it for the second one, set y equal to 0, add 1 to both sides, and divide both sides by 2. So the y-intercept for that line is a half. It crosses the x-axis at a half comma 0. And for the last one, minus 3x plus 5 equal to 0. We can do this a couple ways. We can either bring the 5 over to the left, get minus 5. The way I prefer to do it actually, though, is to add the 3x to both sides. That way we don't have to divide by a negative. You always make more mistakes if you divide by a negative. So now when we divide by 3, we get 5 over 3. So this has an x-intercept of 5 over 3. The line crosses through the x-axis at 5 over 3 comma 0. Now, unless the line is horizontal and therefore parallel to the x-axis, there is always going to be one and only one x-intercept. Now, let's think about some expressions from the last chapter, rational expressions, like 1 over x plus 3, or 1 over 2x minus 1, or 1 over minus 3x plus 5. So what are the restrictions here? If we just saw these, and regardless of what we were going to do with them, one of the first things you should always do with rational expressions is think of the restrictions. Well, the restrictions occur when the denominator is equal to 0. So you're essentially doing exactly the same thing as we did right above, and you're setting that expression equal to 0 and then solving it for x. So for the first one, the restriction is x is not allowed to equal negative 3, because obviously if x is negative 3, that expression, the denominator, is equal to 0. And same thing here in the middle. The restriction is x is not allowed to equal a half. And in the final one, the restriction is x is not allowed to equal 5 over 3. And there's obviously no coincidence here that the restrictions are the same as the x-intercepts, because you can think of that expression x plus 3 as being equal to 0 when x is equal to negative 3, and similarly the denominator would be 0 when x is equal to negative 3. Now, the functions that we're going to be looking at in this section are the ones above. So for instance, what does the graph y equal to 1 over x plus 3 look like, or y equals 1 over 2x minus 1, or y equals 1 over negative 3x plus 5? Well, we know for sure there's not going to be any point on the graph when x is equal to negative 3 in the first case, or x equal to a half, or x equal to 5 over 3 in the other two cases, because if we try to plug in those values, we're not going to get a y value. We will get y values, though, for every other x value that we plug in. Now, these functions are fundamentally quite different from the functions you've graphed before and dealt with before, which were polynomial functions. And polynomial functions are sort of fairly well behaved, meaning they don't really move too quickly. Whereas these functions aren't quite as well behaved, and therefore they're a bit more problematic for graphing on a graphing calculator. There's a couple of problems that arise with graphing calculators. And so for that reason, it's even more important that you get familiar with some graphing software. So I'm going to switch over to Desmos and just explore what happens with these functions. So I'm going to start off with a basic line. And instead of graphing the line as y equals mx plus b, I've graphed the line as f equal to mx plus b. So when you want to use a function notation in Desmos, you don't write f and then bracket x, close bracket, in other words, f of x. You can just write f, and it treats it like a function. But at the same time, it also treats f like a variable, and you can see that I'm graphing I will be graphing in the fourth line there, y equals 1 over f, which is going to be these reciprocal functions, which is 1 over whatever the line is, whatever that linear function is. Now, the initial values for m and b are 1 and 1, so really this line that's being graphed here is y equals x plus b, or f of x equals, 1x plus 1. So it has a slope of 1, it has a y-intercept of 1, and if it's y equal to x plus 1, you ask yourself, when does y equal to 0? Y equals 0 when x is equal to negative 1, and you can see that on the graph. It crosses through the x-axis right there at negative 1, 0. So, what does the graph of 1 over x plus 1 look like? Well, let's take a look. Now, this, as I said, is a shape you haven't seen before. But it's a very easy shape to understand. It has a special name. It's called a hyperbola. And all of the reciprocal functions that we'll be graphing in this section are hyperbolae. And so they're going to have different, they're going to look a little different, but they all are examples of hyperbolas, or hyperbolae. And we know that there's no point to graph when x is equal to negative 1, but it's not entirely obvious that that's true. We could, zoom out a long way, and it certainly looks like the function just zooms up on the right and it zooms down on the left. It's a little bit difficult to verify, but there is no point anywhere on this graph that has an x coordinate of negative 1. Now, keep in mind that the reciprocal function is the black. The line y equals x plus 1 is in red. So if I eliminate that, you can see the hyperbola. But it's useful to have the linear function there, because it helps you really understand the behavior of this. Because for every single x value, the line has a y value, and all you're doing for the reciprocal function is taking the reciprocal of that y value. So for instance, here at 0, 1, the y value is 1. Well, the reciprocal of 1 is 1, and that's why the reciprocal function and the line share that point. And that actually is always going to be the case, because the reciprocal of 1 is 1. The only other place where that's going to be true is down here when the y value is negative 1. And that occurs, for this particular example, when x is equal to negative 2. Now, this behavior of the function sort of blowing up at the point negative 1, to help you understand that, think about what's happening as I go from right to left. So as I move closer and closer to negative 1, the y value is getting bigger and bigger. Why is that? Well, it's because I'm trying to take the reciprocal of y values that are getting closer and closer to 0. So for instance, right there, the y value is a half. The reciprocal of 1 over 2 is 2 over 1, and you can see that point right there. If I go a little further down, see if I can get right to a quarter. So at negative 3/4, the y value is a quarter, and that would correspond to -3/4, and the reciprocal of a quarter, which is 4. So as you get closer and closer to 0 on the line, you're taking the reciprocal of numbers that are closer and closer to 0, and they are larger and larger. And so you get this behavior where the function blows up. Now, the reciprocal of a positive is always positive, and that's why the hyperbola is positive wherever the line is above the x-axis. But on the other side of this x-intercept, the line becomes negative, and so every point on the hyperbola is negative. Let's take a look at an example right here. Again, we're at -1 1/4. The y value is -1/4. The reciprocal of -1/4 is right down here, -4. When the y value has a value, y coordinate has a value of -1/2, the reciprocal of that is -2. And again, it crosses at -1 because the reciprocal of -1 is -1. Now, as you go further and further away from this x-intercept, now the line, x plus 1, has y values that are getting further and further away from 0. So for instance, here the y value is -4. The reciprocal of that is -1/4. And same thing's happening on the other side. When you have, let's say here, a y value of 3, the reciprocal of that is 1/3. It's hard to get exactly. There we go, 1/3. And the further away you go, the closer and closer the hyperbola gets to 0. It's never actually going to hit 0, though, because even if we go 1,000,000 units to the right, the y value will be 1,000,000 plus 1. And the reciprocal of that is still going to be positive. It's going to be very, very close to 0, but it's still going to be positive. So this hyperbola has special behavior that we call asymptotic behavior, which means that in a certain place, the function gets closer and closer and closer to a straight line. As we go far to the right and far to the left, the function gets closer and closer to the x-axis, which the equation of is y = 0. And so we refer to that as an asymptote. Similarly, there's a vertical line, and I can graph it. It's actually the vertical line that passes right through the 0 there. And it's x = -1. As we go, as we get closer and closer with x values to -1, the function gets larger and larger and larger. Now, if I zoom out, you can see that the further I zoom out, it actually looks like the function becomes that vertical line. But we know there's no point corresponding to an x value of -1. So we know it'll actually never touch that vertical line. So this hyperbola has two asymptotes. It has the vertical line, x = -1, and these reciprocal functions are always going to have a vertical asymptote that corresponds to the place where the line passes through the x-axis. In other words, it corresponds to the restriction. And they will also always have a horizontal asymptote, which will always be the same, y = 0, or the x-axis, in other words. Now, let's just see what happens as I change this. If I change the slope, better zoom out a little bit. If I change the slope, it doesn't change too much. Notice that the 1, 0, and in fact down here, this point of intersection where the y value is -1, those points, the x values change, but the y values never change at the intersection because the reciprocal of 1 is always 1. Now, if I change b, it shifts everything. And you can see again, you've still got the intersection of the line and the hyperbola with y value of -1, y value of +1, and you still have that vertical asymptote passing right through the same point as the x-intercept of the line. If I make the slope negative, all that does is it changes the orientation of the hyperbola. Now the hyperbola is positive on the left because the line itself is positive on the left, and the hyperbola is negative on the right because the line itself is negative on the right. So once you understand this behavior, it's actually pretty easy to sketch these functions. In order to sketch these functions, the first thing you do is you figure out the restriction. In this case, we've already done that. It's x equal to negative 3. You then draw a dotted line corresponding to the asymptote, the vertical asymptote. So that is the line x equal to negative 3. And I'll put it in curly braces just to make it clear that it's a line. You can, and this is actually something I suggest doing, you can graph the line itself, y equals x plus 3, just to keep it straight in your head that this line has a positive slope, which means that the reciprocal function is going to be positive on the right. And the quick sketch looks like this. You could label some points, these points of intersection of the hyperbola and the line. Certainly easy to tell what the y-coordinates are. They are negative 1 and positive 1. The x-coordinates you could just figure out by substituting those y values. I'll leave that to you to do, because all we want really here is a sketch, quick sketch. And again, that green line that we graphed is the function y equals x plus 3. Let's try the middle one here, quick sketch. We'll try graphing the line first here in green. Y equals 2x minus 1. So it's got a bit of a steeper slope. And we know that it passes through the x-axis at positive 1/2. So we can draw a vertical asymptote right there at x equal to 1/2. And wherever the line is positive above the x-axis, so will the hyperbola be. And so that's your graph, quick sketch of the reciprocal function there. And let's try it again for the third one. So this one, the line y equals negative 3x plus 5, has a negative slope, positive y-intercept. So that's the line y equal to negative 3x plus 5. And it passes through the x-axis at 5/3. So that's the line x equal to 5/3. And because the line is positive on the left, so is the reciprocal function. And on the right, same, because the line is negative, the reciprocal function is negative 2. So what kind of things are you going to be asked here? Well, you're going to be asked for the domain and range. You're going to be asked for the equations of the asymptotes. Now, the domain is essentially this statement right here. You can plug in any x value you like except for negative 3. You will get a y value as long as you don't plug in negative 3. So essentially, you've done the domain. And the range is actually really easy. The range for all of these reciprocal functions is just simply y is not equal to 0. Because you can see that you're never going to have a place where the hyperbola touches the x-axis. But the functions blow up. They head up towards positive infinity and down towards negative infinity. So every y value is possible with the exception of 0. And the equations of the asymptotes are also pretty easy because every single one of these has a horizontal asymptote, the spelling of which is as follows, asymptote. So every single one of these has a horizontal asymptote, which is just simply y equals 0. Which is the equation of the x-axis. And then each one has a vertical asymptote that corresponds to, again, the restriction. So if you've got the domain, you can write the equation of the horizontal asymptote. And I've done that for each of the 3 cases. X equals negative 3 is the equation of a vertical line that corresponds to the vertical asymptote for the first, x equal to 1/2, and x equal to 5/3 for the second and third. Now, it's important to keep in mind that the asymptote and the equation of the asymptote are just more descriptive factors. They are not the function itself, but it tells us how the function behaves. And so if a function has an asymptote, it means that it gets arbitrarily close to that asymptote. And this is actually a calculus concept you'll explore in much greater detail. And this idea of a function getting arbitrarily close means that you can't ever specify how far away the function is from the asymptote. You can say for a particular point how far it is from the asymptote, but there will always be another point where it's closer, and it'll just keep on getting closer and closer and closer without actually touching it. Now, later on, we will see some examples where the functions actually cross through the asymptote, but they're not behaving asymptotically at that point. So this function, and in fact, all of these reciprocal functions are behaving asymptotically when you go far to the right or far to the left, and when you get really close to that restriction, that point where the line crosses through the x-axis. Elsewhere, they're not behaving asymptotically, and we don't have to worry about the asymptotes, but the asymptotes essentially serve to tell us what happens in the extremes.